I will introduce our next speaker. I'm pleased to introduce Gerhard Klimeck, professor of electrical and computer engineering at Purdue University, as well as the director of Network for Computational Nanotechnology and really director of the Center for Predictive Material and Devices. His research interests include nano-electronic devices, device analysis and development, high-performance computing, and engineering tool development. Today, he will present a talk titled Mythbusting Today's Nanotechnology and Knowledge Transfer Through Nanohub.org. Please take a moment to silence all the electronic devices. Thank you and enjoy. By the way, if anyone have any question in the end, you can ask the speaker in the microphone at the front. Thank you.
So good afternoon. Thanks for coming for this presentation. I would like to highlight various items that are down the line on the technology roadmap that are geared towards robots and computing, and give you some perspectives as to what is feasible today and what's feasible in the next few years. And then also tell you about all the things we were told we couldn't be doing in the last 12 years and see how you can overcome various issues there. So I'd like to start out by thanking the people that are involved. So this is my research group, a picture of it from a few years back. You have to thank all the funding agencies that actually allow you to do this kind of work here in a research university. And on this presentation in particular, Matthias Tahn really helped me a lot with some of the slides and making them really well visible, etc. But there's another group of people that need to be thanked. That's the Nanohub team, the NCN team, that is really creating this website, nanohub.org. And without them, that wouldn't be possible either. And the third group of people that need to be recognized are all the people that actually contribute in this website. So it's somewhat different than a normal faculty talk in that there's really different groups of people involved in all the work that I'm representing here. So let's think about what happens when you're ill-informed and maybe you have fears. Technology can seem rather dangerous, and you've seen images about GMO, and it's a fact of life that we overact when we don't know, and that's why we have to study the effects of various technologies. So what you want to do is not just have myths, but really try to get down to the facts. And for nanotechnology, some people think it's dangerous. Certainly it's unknown to them, and it might be far in the future. So let's look at some of those items and explore them. So certainly, if you look at popular media here, X-Files from a few years back, right? Nanotechnology depicted as an evil thing that takes over humans. There is certainly also literature, science fiction literature like Prey. And actually on Wikipedia you can find an article that lays out a whole slew of these really speculative fiction articles that depict nanotechnology typically in a doomsday type of form. So clearly there could be an issue with poisonous materials that could be in our lungs, that could be in our body. So those are quite some serious concerns, and one has to look at those, and that is actually also happening. So the National Science Foundation, as part of their $1 or $2 billion effort per year, is sponsoring center-level efforts that take environmental impact of nanotechnology serious. So here's an example of a center at Arizona State that is dedicated to examining toxicology effects of nanotechnology. There's also an issue on societal issues, and they're being taken serious as well, and people study that, and it's again a center-level effort, and Here's one example again at ASU. And they have a virtual institute that brings scholars together. They even now have a way of publishing their results. So it's innovative in the space that we normally don't think about, and that is really the National Science Foundation taking a step forward to inform the public, to have arguments as to whether something is safe or ethical, and have that be thought through rather than being afterthought. There's also a real effort on global service for research and education, and that is an effort we have here undergoing at Purdue, where we really have a global following, where we allow people to learn about nanotechnology and get informed and learn about it and integrate it into their curriculum and into their research. So I would just strike off that we're not taking it lightly, that it might be dangerous, and we're examining it. It shouldn't be unknown. We have efforts to enable people to learn about it. And let's go to the third myth, that it's going to be far in the future that we have nanotechnology. So let me, before I take you in the future, I'll take you in the past, to the past. So the year 1965 it's a very important year to me very personally. I was born. So, but more importantly, somebody sketched something into his notebook. This person is Gordon Moore, co-founder of a company, small company called Intel. And he really had 3 data points, and what he predicted was that it's an economic law that the number of components per integrated circuit can be increased exponentially, and yet the relative manufacturing cost can go down. Has little to do with technology as such. It is actually an economic law, and it needs to be economically viable to make these chips denser at a lower cost. And interestingly enough, from a few years of data, he predicted something that has lasted over 40 years. So if you look at the data from 1970 and count the number of transistors that are on a chip, you go up exponentially here on this exponential or log scale over the years, and you find that today we have over 1 billion, close to 2 billion transistors on a chip. Now that's a reasonably large number, and to put that in perspective, that's a third of the world population working together in a cohesive form without having a war. So it is an engineering marvel of independent elements. Well, they're not all independent, but controlled elements that can actually perform an action together and do something constructive. On the same time, the technology that enabled that was to make it smaller and smaller. So the transistors have gotten smaller over the years, and alongside that getting smaller, the dollars spent per transistor is also going down exponentially. So from 1971 to 2012, the price per transistor has dropped by a factor of 50,000. Now, if you look at any normal economic good, a dozen eggs, a car, a washer, you would never dream that such things would become cheaper and cheaper by a factor of 50,000, right? There's inflation, and you can adjust for that. But basically, there hasn't been technology innovation like that, where technology has gotten faster and better and cheaper by factors of 50,000. That's quite an amazing number. So, what might be also surprising to you is that nanotechnology is actually here today, where today's transistor that Intel ships in their advanced chips, CPUs, the 22 nanometer tri-gate transistor, has a gate length of 22 nanometers. We'll talk a little bit more about that later. If you scale that into a red blood cell, which is about 7,000 nanometer large, you can see how small this device actually is. And this is a shipping product, right? This is nanotechnology by its definition. There's actually, in this case, 3 dimensions that are smaller than 100 nanometers. So nanotechnology is here today. It's not far in the future. You have it in your pocket, in fact. So it's neither far in the future nor is it really unknown, and also we are studying whether there is danger. So there could be actually a perspective for dawn, right, rather than just doom. So let's look at some scenarios of dawn. So if you have a smartphone in your pocket or something alike, or an iPad, you carry one of the world's fastest supercomputers in your pocket from the year 1985. That's one of the technology advancements we are experiencing, right? This is quite amazing what these devices can do. And here's an A5 chip here in an iPhone. This is nanotechnology in the chip itself, so it's shipping, it's in your pocket. And just to put that in perspective, if you look at the global demand for semiconductors, it's today roughly a $300 billion market, and it has grown dramatically over the last 10 years, where it was roughly 160 in 2003. The rest of the world demand has sort of stayed flat. America's also stayed flat. In China, the market has grown dramatically. So the growth really has happened in China. But overall, it's a $300 billion industry that is really driving a large part of the economy. So if you look at the economy on various countries, the electronics industry is in the 4 largest economies in the world. In the US, it's 700 billion. In China, 702 billion, 1,600 billion in China. In Japan, 418. In Germany, 148. And if you look at that as the percent share of the gross national product or gross domestic product, it's a significant percentage. In China, it's 20%. In the US, it's 4%. In Japan, 7%. In Germany, 4%. So the microelectronics industry is a major economic factor in the life we live, in how we create wealth in our society. If you look at the individual companies, you can see that the US is one of the largest suppliers of nanotechnology. So here, Intel, 47 billion, Qualcomm, 17, Micron, 14. So Samsung in Korea is a huge company. It actually has something like 20% of the country's gross national product. Those are not small industries, right? This is impacting a whole society and how we live. And how well that goes forward and how wealth is being created in these societies depends very strongly on this technology, on making it faster, better, cheaper all the time. Otherwise, why would you buy another computer in 3 years or 2 years if it doesn't do anything more than your old device had, right? So that is, the advancements is what we buy. All right, so nanotechnology is in your pocket. It changed your lives already, and it has global impact. It has a global relevance. So let's have some other examples that might be in the future that are reasonably realistic, that bear nanotechnology in it. I'll give you some examples of prosthetics that are mind-controlled, so you can have more complicated robots that are connected to humans. You can think about water desalination with nanomaterials, where membranes are well constructed in order to create drinking water. Solving clean water problems in the world is a very critical thing to be done. There's millions of people dying just from spoiled water or water that's contaminated. Today we use night vision goggles, maybe only for military because it's really expensive and it's very special. But what if you could equip yourself, even on your, like a contact lens on your eye that is providing you night vision? Maybe you can drive safer at night as well. Maybe you can embed it in a car, and it's more technology that anybody can have rather than specialty people in the world. All right, so there's the dawn aspect to nanotechnology that's not too far in the future, but it could be really impacting us even further. So let's look at some of the computing myths that are out there, that computers are about to surpass us as humans, and that the computers will become ever faster and faster. So let's explore some of those. Maybe you've seen charts like this one where people compare the calculations per second per $1,000 spent as they go up exponentially with Moore's law, and how they approach the say calculation level of the brain of a mouse and a human brain. In a similar chart here, somebody looked at millions instructions per second for a single CPU, and again, it's growing exponentially over the years. Here's the processing power still. Here's the number, is the megahertz rating, so the speed of the CPU. We'll talk a little bit about that. But basically, it is getting closer to that, what a human mind is estimated to have. But if you now look at supercomputers, which are basically an aggregate machine of many, many cores, these are typically a factor of 10,000 to 100,000 more powerful than what a single computer like your laptop can do. So let's look at some of those supercomputers and what they do and how they're being consumed. So here I have a chart of the usage of supercomputing that is increasing exponentially. And this is really the aggregate floating point operation consumption of what people use in research and development. So here, if you look at 1 million gigaflops, that's a petaflop. That's in about 10 years ago, that is what was being consumed. Today, you can buy single computers, not all of the computers of a nation, but a single computer that can run at a petaflop of almost 10 petaflops. And I'll show you an example of such a machine. But overall, all the strong economic countries are using these supercomputers to solve technical problems. All right, so in my research group, we are using some of these supercomputers as well to solve technical problems. We've developed a software we call NEMO. We work in computational nanoelectronics, so we try to understand these miniaturized transistors and how electrons flow through them. And we built up the software in some 18 years overall of my personal experience when I was at Texas Instruments and then at NASA JPL and now at Purdue. And one of the incarnations is the Omen code that was developed here at Purdue as well. And this is the first petascale engineering code. So let me try to explain this chart to you. So when you take a program and it takes an hour to run, and you put it on 2 CPUs, you'd like to have it run for half an hour, right? You put it on 4, then a quarter of an hour. So if you put this code on a computer that runs on 220,000 CPUs for about an hour, it scales perfectly ideal to the point if you just ran it on a single CPU, that program would run for 25 years. So clearly, you would never run it. Number one, the computer wouldn't live that long. And the point is we can do real engineering science and designs on a computer like that and having a software like this. And it's a tremendous breakthrough to have done that with a general tool that can allow the design of transistors. And it was awarded with a Gordon Bell honorable mention at that time because the Japanese had the bigger computer, so they could run a program that was even faster, and that's what won the competition. But either way, this is the first engineering code that runs at that scale. So, but what I want to highlight is that what this code does is not even close to what a human brain can do. It just solves partial differential equations that help us understand how electrons flow, but it has no decision-making capability at all. Yet, it's a very sophisticated engine that is very useful to us. And it runs on a computer like this. This is actually the successor of the previous machine. It's roughly twice the size now of what we ran on. So this now has over 560,000 cores, and it can develop these 27 petaflops per second. And it has a small power consumption of 8.2 megawatt, which means it's roughly 600 600 US households. And it's roughly the size of a football field or half a football field, quite big, requires an immense amount of cooling and obviously an immense amount of power. So let's compare that to a human brain. By some estimates, you can argue now that the human brain is roughly 37 times faster still, but it's no longer factors of 1,000, right? So it's pretty close. But look at this here. Compare the speed. We have just done this here with 37 a factor, but the human brain roughly consumes 30 watt, and the Cray Titan consumes 8 megawatt. It's quite a different number, right? And if you look at Moore's law again, we keep looking at, wow, we're getting faster and faster, more and more throughput, but we also crank up the power density that is being consumed on these chips. So, but we're happy, right? We get faster computers, and we work that way from the early years over here to get more powerful computers. But now put that onto the scale of having a human brain and its energy consumption down here. You can see that really we've been marching along the wrong direction all the time. Instead of getting down to low power devices and low power architectures, we've always pushed in the other direction to get more power. So really the solution is a very different architecture, a very different way of assembling these computers together, possibly even with different devices than what we use today. So there's efforts like this. Here's an example from IBM. Recently they had a very nice science article where they built a machine at today's capabilities with 5.8 billion transistors, but what comes out of it is 1 million neurons. So that's not a very efficient brain yet, but it can do things and very fast than what normal computers can do. So it's a powerful research effort, and it really pursues a new architecture, a new way of looking at computing, and that might get us closer to brain-like activity, but it's not going to be the standard supercomputer that we have installed today at various places. All right. So as for now, computers are pretty far away still from surpassing humans. Let's look at this next myth here. Computers will become ever faster because they have done so over the last 40 years. So, it has to continue like that. So let's look at Moore's law again. Here's a nice graph that I took from the Free Lunch is Over. You can Google it. And it was updated in 2009, so the data is some 5 years old, but it's pretty telling. So here in red, you see Moore's law going up. That's the number of transistors that is still growing, and per generation that we create these devices. But if you've been buying computers lately, you might have noticed that for the last 8 years or so, the CPU cycle, the megahertz or gigahertz rating has not changed. And in fact, some computers, it has gone back down. So basically, the computers are no longer getting faster. And they roughly have pegged around 100 milliwatt power consumption, 100 watt power consumption. So that seems to be somewhat of a magical number. And overall, the performance gain has sort of stagnated as well. So in other words, the individual CPUs are no longer getting more powerful, nor are they getting faster. So there's something that is changing significantly. And so that's this myth here, right? They don't become faster, and we have a very serious problem. So let me try to get to some technical detail as to what some of the problem might be. So this is a graph that is basically taken from an Intel presentation in 2004, which was very eye-opening to many people. So here that person, Pat Gelsinger, had plotted the power consumption, the power density per square centimeter that's being consumed in these chips as a function of years, and then it crosses this magical line of 100 watts. So what's so special about 100 watt? So a hot plate is down here at 10. A nuclear reactor has about the power density of 100 watts here. and the rocket nozzle is at 1,000, and the sun's surface is even higher. So obviously, at some point, your chip will just melt, right? So this was sort of an eye-opener to many people in the community that clearly stated we really can't get a lot hotter than we're operating today. So there's a foundational problem in power consumption in this electronics. All right, so where's this power being consumed? So if you're not an electrical engineer, just forget about this little inverter sketch here. No need to really understand it in detail. The point is, there is two types of powers that are being consumed. So this is a circuit which basically holds a logical 1 or a 0. And whenever you switch it from 1 to 0, you do that in a certain cycle time, a frequency. You have to charge some capacitors, that's this capacitance here, and you charge them up with a voltage, a supply voltage, and it goes with a square of that voltage. So the dynamic or the switching power goes as the frequency, the capacitance, and the voltage square. So that's where the power is being consumed. So if you want to now reduce the power, you can say, well, we reduce the frequency, so your computer will run slower. And that, in general, one would think is not such a good choice, right? So you could reduce the capacitance here. That seems like a good choice, but it's very hard because you have to make these things smaller and smaller and smaller, and that's what we've been doing, and it's getting more expensive to do so, and I'll talk a little bit more about that. Or you can reduce the voltage, right? It even goes as the square, and you get a big smile on your face and say, great, we can reduce the voltage. And if you do that, you need to look also at the second type of power that is being consumed. Not just when this device is switching, but also static. If it just holds a 1 or it just holds a 0, what kind of power is consumed? That's the so-called off-current or leakage current, and it happens. It so happened that it goes with the exponential of the supply voltage, meaning you reduce the voltage, you're really going to blow up your leakage power. And let me try to explain that to you sort of as a cool way to look at transistors. So maybe that's the one technical item that's part of this lecture. So here is a standard transistor. We call this a source, this a drain. Here's a gate voltage. You can think of that as a valve. And in the source, you have a bunch of electrons. These bunch of electrons, they live in an apartment complex that has these holes, and since the electrons are quantum mechanical particles, only one electron per apartment, one quantum number. And this is a weird apartment. It actually gets bigger and bigger the higher you go. That's called the density of states in a semiconductor. But either way, the higher you go in energy, the more apartments you have. But on the other hand, it takes a lot of energy to go up there. That's the thermal energy in the system. So only fewer and fewer electrons live up here. So there's sort of an exponential decay in the number of electrons, even though there's more and more open apartments up there. And then there's this gate voltage here. And this gate voltage is regulating the flow from the source to the drain. So as soon as you apply a voltage between source and drain, that's what this is, you're going to have some leakage. You're going to have some electrons that will flow, because there's some guys that are going to be up here in the thermal tail. So there's going to be some leakage, and there's going to be current flowing, even though you think your device is off. That's called a leakage current. That's the current you don't want. Now you're going to turn on your valve. That means you lower the barrier here, and you allow more electrons to flow out. You lower the voltage again. So you get a certain slope here, and I'll talk a little bit more about the slope in a second. So you lower the barrier again, more electrons flow, you lower it again. At some point, you're going to get all the electrons that can go in the ideal world. So that's really the essence of a transistor, a switch. It's a variable resistor. And you get a curve like that in the ideal switch, right, what you have in the wall, it's on-off, right, 0 or 1. But a real switch really turns on over a certain voltage range. It's not just digital. There's a range. And that range is really determined by the slope that you can get here. And you can do some analytical work and show that slope really depends on Here's the number of apartments, that's called the density of states, and here's the occupation of these apartments, that's the so-called Fermi function, and that's an exponential decay with a function, as a function of temperature. And then you can do a little bit of analytics, and you can find that 60 millivolt per decade is the smallest slope you can have here. And that has just to do with the way that you have sort of an open distribution of carriers up here, and you gate them with sort of a valve that is always open to the top. So you have no chance of escaping this thermal tail, and that thermal tail means I will always have a slope that goes like that. I will not have a curve that will go steeper than that in a device like that. It's a foundational thing. It's not like I made that up, I take it from the community, that's how it is. All right, so if you have this ideal switch, and by the way, typical switches have a subthreshold swing of 70 or 80, so they're actually smoother, they're not as steep. So if you take this ideal transistor and say, I want to reduce this voltage here, all you're going to do is shift the curve over, right? You're going to just move this curve over, and if you do that, then this intersection point here goes up on this scale, and notice that that isn't a log scale. So that means your leakage is increasing exponentially, meaning your device overall gets worse and worse, and you're going to heat up the device even though you're not doing anything, you're not switching. And that is seen in the technology data that we have today. So here's the leakage current, and here's the dynamic power, and they're intersecting today, meaning unless you do something in your circuitry, whether you operate the computer or do computing on it or not, it's consuming the same amount of power. It's a good space heater. So that's a bad thing, right? You'd like to have a technology that consumes energy when it's being operated, not just when it's sitting there idling. So there's more complicated circuitry that is now being built into these computers such that you don't have such a heat generation. But either way, we're stuck with this, and what we like to do is overcome this, right? So that what we really want is something like this, not just shift the curves, we would like to bend the curve over to make this steeper. So that's the more ideal switch, where it goes from off to on in a very small voltage. So the work you have to do to make that switch go would be smaller. So that's what we like to do, and there's some concepts out there that allow us to do that, where the culprit here was the thermal distribution of these carriers, and you can place that here in the band gap of a material, and then modulate the band gap here under the gate, and then electrons can actually tunnel through this device. So there's actually hope to create tunneling devices that are functioning very different from a normal charged transistor that you have in your products today. And then you can reduce the voltage. So the point is, this hunt for Red October, I mean this new switch, is actually on. And it's on in a big way. I mean, all the big semiconductor companies are involved. They built consortia where they funnel money to research institutions like Purdue, and we are involved in studying this type of material and these type of devices, and that's what our research group does. So the new NEMO 5 version that we have models these kind of devices for us to work with experimentalists. So the goal is really to make these devices run faster than the standard CMOS. So here is a paper by two people from Intel that have explored all of these different devices that are out there that supposedly might replace this new transistor, this old transistor. And they plotted in terms of switching energy and delay, and basically the good corner is down here. You like to switch really fast for very little energy. Over here, you would switch really slowly for a lot of energy, right? That's sort of not where you want to be. And there's a few devices here that seem to beat today's CMOS devices, and that is what's being pursued in these tunnel FETs. But overall, it's still going to look pretty bleak, because only for a little while will we have a chance to make these devices faster and consume less power. And let me show you why. There's really a fundamental limit and an economic limit to this scaling of Moore's law. Let me talk about the fundamental limit first. So you've seen these charts now where there's so-called nodes, 32 nanometer node, the 22 nanometer node is being sold right now. 14 nanometer node was scheduled to arrive in 2013. It's 2014, it's not on the market yet. So you can already see a delay in these devices showing up for consumers. And what's out here in the 10 or 7 nanometer realm is really unknown on what kind of devices are out there. But let's look at this so-called 22 nanometer node in some more detail. It's a transistor that is very different from what I sketched before, which was planar. It's actually a three-dimensional object. It looks like a little fin, and there's a metal wrapper around it that allows you to be the gate. That's the valve. And this is a sort of a TCAD model, like a solid model. But if you look at a cross-sectional image here, scanning electron microscope, what you see is here's the fin, and here's the metal around it. But notice that this fin is 8 nanometers wide. So it's very thin this way and relatively long, 22 nanometers long here in the metal. So what does that mean? Let me translate 8 nanometers for you. 8 nanometers is 64 atoms. That's pretty small. If you look at the 22 nanometer length here of the gate, that's 176 atoms. Also pretty small. If you just look at the cross-section here, that's sort of in the active region, it's just 1,000 atoms. So what I'm repeating here is the word atom. All of the tools that are out there commercially available today that help us design these type of devices don't even know that atoms exist. They live in the world of a continuum matter that you can cut in half and cut in half and cut in half again, and that there's a discrete nature underneath is not even comprehended in these tools. And that's why we're working with some of the bigger semiconductor companies and the biggest semiconductor companies to really work with them, understanding these devices and building tools that they can actually use. So let me go to this beautiful chart here, right? Let me translate the 22 nanometer node into number of atoms. So 176, if you go down to a 5 nanometer node, that device would be 40 atoms long. I make this term critical atoms. So that's here in this cross-section. We know it's roughly 64. We're not quite sure how the geometries will be, but it's going down to teens of atoms. Very small number of atoms in the cross-section. And what's even more amazing is that the number of electrons that are going to sit under this gate that operate this transistor is going down to the tens. Very different from having 1 million electrons, where it doesn't matter whether you have 1 million or 1,000,001, but it's going to make a difference whether you have 15 or 16. So your device might be pretty noisy. It might be operating very differently than what you think. Here's a little mention again, right? This is why we build this tool set NEMO, that we can understand these devices from an atomistic sense and simulate real devices still. But this trend of number of electrons going down is pretty old. In fact, this chart I'm showing here, I've used for the last 15, almost 20 years, because what I'm showing you here is number of electrons going down exponentially with the roadmap for the semiconductor scaling. But there's a whole world out there that is dealing already with devices that have only a few electrons in them. They're called quantum dots, and that's some research I've been involved with for the last 20 years to study what happens with devices where there's only a few electrons. Can you make devices out of it? Can you make circuits out of it, etc.? And so the roadmap is heading for a finite number of atoms, which is interesting, I think, certainly from my perspective. And in 2008, we had a nice paper in Nature Physics that actually documents that there is electron flow through single dopant atoms that control and influence the electron flow. So that was very interesting work, and I think breakthrough work. And then we continue to work on devices where an Australian group is actually purposefully putting individual impurities down into the silicon. And we had wires, looked at wires, for us theoretically, for the Australians experimentally, where there's wires that might be 4 atoms wide and 1 atom tall, and electrons flow through it like in a metal. And then we went to a single atom transistor, and this was in Discover magazine as one of the top 100 inventions of 2012. So, punchline here, I'm sorry. This is the physical limit of Moore's law. You're not going to make transistors smaller than that. Right? In the way we think about charged transistors of charge hopping in, charge hopping out, the smallest bucket you can imagine is that one of one single atom. But there's another limitation that we're seeing already, which is the number of transistors you can produce per dollar. And it has been growing nicely, exponentially, but now it has actually flattened out. And remember, Moore's law was actually an economic law, meaning even though we can make a single atom transistor, it may not be economically viable to do so. So you may never get this kind of a device in your pocket, not the one we've made at any rate. You need like deep cooling for that. But at any rate, you can already see that maybe Moore's law is ending just for economic reasons. All right, so there's a fundamental limit, there's an economic limit to these transistors getting ever faster and ever smaller. So the doom picture I have in here, if we have a $300 billion industry that does not advance into new technology every 2 years and lets us throw away our devices from 1 year to the next or every 2 years, we're going to have a change in our global landscape on economics. We will change how we create wealth. Suddenly, these transistors are no longer advanced technology. They're becoming, missing the word, like grain or salt. It's just a commodity. That's the word. All right, so if that happens, will we have an economic slowdown, which will in fact affect all of us? And that is not too far in the future. All right. Now, I talked a lot about nanotechnology, had one technical example. Where do you learn about this stuff? And can you share that knowledge? I've shown how we make structures smaller, put billions of them together. We have research investments in the US of $2 billion alone into nanotechnology. The question is, can we put that into people's hands? Can we make it useful? And that really was a vision from the year 2002 by Mark Lundstrom here at Purdue to create what we call today really a new science cloud, where we can share these tools with others. And the goal really, or the services we would imagine at the time, or did imagine at the time, is modeling and simulation software delivered to everybody in the world without them installing anything, having seminars, tutorials, and classes. And the goals for doing that is really knowledge transfer, to get the stuff seen by others and make it useful. The second goal is really knowledge generation, enable other people to generate new knowledge. And then also have economic impact, advance economy and interact with industry, and have professional development, that we really have a new community that is forming. And ultimately today we would have to say we now have software as a service. It's a new delivery mechanism that we have in Nanohub. So this is what we have today. We have a global service of Nanohub users here in the week of February of last year. Nanohub never sleeps. We have new registered users, simulation users, tutorial users. Simulation users, roughly 13,000 per year, 20 times more tutorial and lecture users. It's really becoming a global community. It's worthwhile looking into that as an integral picture over the year, over 1 year. Basically, wherever there's a civilization that has enough energy to light up the night sky, we have Nanohub users there. People are interested in nanotechnology. They want to learn about it. They need to have high-quality material where they can learn from it. We had nice publications in Nature Nanotechnology describing this, learning and research in the cloud. but it's more than academic. It's more than a website. I'll show a brief video. These are visualizations anybody can do on Nanohub. Here's an STM tip. You can explore new theories or existing theories with tutorials and lectures. You can simulate, which is really the key element, just with a click of a button. You don't have to install anything. You can run simple tools like this one and rather rapidly visualize, say, a carbon nanotube. And you can run very sophisticated tools that could run for a couple of hours on a big supercomputer, and the user is really just oblivious to that. Sophisticated visualizations. This is a biopore where ions will flow through the pore. I'm going to run out of time, so I'm going to skip forward and just tell you about all the things we were told we couldn't be doing over the years. So 12 years ago, over the last 12 years, we heard you really can't support all of these developers. You can't deliver to users. And you want to run an infrastructure at a university that's done by other people. The challenges I'll go over here as well, but really the key element, the key insight is you have to think of those groups as entities or stakeholders with different interests. You have suppliers, you have customers, and you have a market. And those are the things you need to support. And that is what we've done with Nanohub, and I think we solved a lot of the problems. And I'm going to go into supplier side, where the suppliers are now individuals that are software developers. We have over 380 people. Most of them are not paid by us. And they're linked by these white lines with tools that they work on together. So they really form a social network. So we have a supplier network, and the number of developers and the number of tools is growing nicely. But these tools are actually evolving over time, and there's new versions. So there's product innovation, if you will, that is happening. So people stay connected. It's no longer the tarball or this old program that sits on a web page, but it's a new cloud service that we have. We are building incentives for young faculty members. Here's a person that used to be in my research group as a postdoc. He then went to Southern Illinois University, and the usage at that university picked up dramatically. He infused Nanohub into existing classes, created new classes, used it for research, and got promoted with tenure within 2 years. That's a pretty fabulous story to hear for somebody. So we're building incentives to participate. And obviously, we can run an infrastructure like that because we've been doing it. I'm not going to go into the details. But I'm going to look at the user side. You've seen parts of the video. It's easy enough to use. I'm going to prove to you now that it's useful in research. And the way we prove usage in research is we look at citations. We look at who is citing Nanohub in the scientific literature. Are these people outside or inside? Are these people in nano? Are they in education? We can even highlight whether there's people that look at experimental data. So really experimentalists use our material as well. So is it used in education? We are studying how people interact on Nanohub and have user-user correlation. So here on the x-axis we have time, and each dot is a user. So here's a group of users that basically comes once in a semester for a week and does their homework. Here's a group of people that use this orange tool in a sort of rhythmic way, and here's spring break. There's another group of users that uses 1, 2, 3, 4, 5, 6 different tools. All of these people are classes. And we identify these people through similar behavior, meaning not everybody told us that they're in a class. Just like you don't tell your web pages where you subscribe to all the details of why, how, when, because you don't know yet exactly what you're going to do there either. So we have to figure that out, but the really cool thing is we've identified over 20,000 students and over 1,000 courses like this. And these people are using research tools, which is a really cool thing. So for us, it's really a way to get research tools into a classroom, and it takes on average just 6 months to do so. So it's very cool in that sense. So let me wrap up my presentation by saying Nanohub is now a Nano App Store. that is running in the cloud. It's really the first science computing cloud. While this sort of sounds simple today, I'm not aware that there's any science cloud like that anywhere else in the world, and we're operating this here out of Purdue. And it's also science software as a service, and really it allows for translational research, putting research into people's hands. So let me go now to a newer vision. This we've done for 12 years. So the new vision is really have interactive journals. So you read your article, you click on the graph, it goes back to the tool that generated it, or you get into the data set that generated these numbers, and you can compare it to your own experimental data to really drive towards reproducibility of data and really get into the day-to-day workflow. I hope I've shown you that nanotechnology is in your pockets today. It has a global economic influence, and Moore's law will end in about 10 years. And new computers, architectures, and switch concepts are needed to get anywhere close to what sort of the doomsday dreaming is. Okay? So there's a whole lot of technology that still would have to change and develop. And it's not just going to be simple computers get faster, because that will not happen. All right. So I'm an optimist overall. So rather than doom, I see a lot of dawn. For Nanohub, I see us evolve into a professional nano society that might have 100 or 200,000 members across the globe and become sustainable for the sake of learning and research in nanotechnology. And at the end, I'd like to thank you for your attention, and also Matthias one more time for helping me with the slides a lot. So thank you very much.